Hello everyone, I am Dr. DP Bora. I welcome you all to my YouTube channel, the Microbiology Digest. Today again I am back with a new topic for discussion, that is microscopy and micrometry. So one of the very important topic in microbiology, in day-to-day working with microbes, microscope is an essential tool for which is used for understanding the different aspects of microbes. So let us first understand the definition of microscopy. So microscopy, simply we can say that it is the use of microscope. And in broader terms, we can define microscopy as the scientific discipline of using microscopes for getting a magnified view of objects that cannot be viewed by naked eyes. So what is microscope? Microscope is an optical instrument, as we all know. It is an optical instrument which can or which are used to magnify or enlarge minute objects or microorganisms which cannot be seen by naked eyes. So, in microbiology, microscopy is used basically for two purposes. Number one, for the initial detection of microbes. Number two is the preliminary or definitive identification of the microbes. So, first purpose is the initial detection and second is the for identification. These two are the primary purpose for which microscope is an essential tool to be used in all the activities related to microbes. Now, as I said, microscopy or microscope, it is one of the essential or very important tool, because without the help of microscope we cannot see the microbes. So that is why it is uh, very important tool used in microbiology. Now let us know how microscopes were developed. So the development of microscope dates back to 1590. Two person, Hans and Zacharias Janssen, they were first to create a microscope. So it was a small simple tube having two lenses fitted in the same tube, and through this they were able to achieve a magnification of maximum 9 times. 9x magnification was obtained. Then subsequently Robert Hooke in 1670, he improvised the microscope and developed a compound microscope. So he used three lenses instead of two, which earlier it was two lenses were used. So Robert Hooke, he used three lenses to achieve some better magnification in comparison to the microscope created by Hans and Zacharias Janssen. Then in 1675, Anthony van Leeuwenhoek, he prepared another form of microscope with better magnifying capacity, which is 270 times magnification uh, could be obtained. And with this microscope, he was the first person to report the presence of microbes in the environment. So because of this, he is regarded as the father of microbiology because of this great invention. Then microscopy as a science, it was developed after the work of Ernst Abbe. So in 1878, a German physicist, he was he successfully developed the theories related to the magnification as well as resolution by a microscope. So he was the first person, Ernst Abbe, he was the first person to use the oil immersion objective in the microscope. Then in 1939, as we all know, it was the uh, development of electron microscope by Noel and Raska, two scientists. So it revolutionized the study of microbes in greater detail. Then subsequently 1951, Nixon and Ellis, they invented the X-ray microscope. Then 1981, Binning and Rohr, they invented the scanning tunneling microscope. This is in brief the history how microscope has developed to the present day advanced microscope from the initial starting part. Now basically there are three types of microscopes. First one is called a simple microscope. It is having only one lens. Then second type is called as compound microscope. It is having two sets of lens. Then third one is called as electron microscope. So here instead of the lens, a beam of electron is used to magnify the objects. So the magnification capacity in each of the microscopes uh, are different. So maximum magnification can be obtained by electron microscope, which has a capacity to magnify up to 3 lakhs times. An object can be magnified up to 3 lakhs times of its initial size. Now let us understand various parts of a microscope. All the components of a microscope can be divided into three different parts. First one is the optical part, which includes the ocular lens and objective lens. Then the illumination part, it includes the light source, condenser, and the diaphragm. Then mechanical parts, it includes the stage, focus knobs, arm, and the base. So different parts in the diagram, different parts have been labeled. So it is very much essential to know the different parts whenever we uh, want to handle a microscope in the microbiological study. So it is very much essential to know the various components, various parts of a microscope. Now in the microscope, while using a microscope, it is very much essential to understand some terms related to the microscopy. First one is the refractive index. So it is the measure of how much any substance can slows down the velocity of light, because microscope is an optical instrument, so it works on the principles of light. So the velocity of light, it gets slowed down when it enters from one medium to another. So the measurement of the slowing down of velocity of light, it is called as the refractive index of that medium. Second is the focal length. So distance between the center of the lens and the focal point is called as the focal length. So in microscope, focal length plays an important role in calculating the overall magnification of a microscope. So in general, a lens with a short focal length, it can magnify an object more in comparison to a lens having a longer focal length. Means if a lens is having a shorter focal length, it will give a better magnification. Next term is the magnification. So term itself, it indicates that it is the ratio of the size of an object which is seen under microscope and its actual size. So that the ratio is called as the magnification. So in light microscope, so magnification is always calculated by multiplying the magnification power of the objective lens as well as the ocular lens or eyepiece. So both the lens magnifying power is multiplied to get a final magnification power of a microscope. Next term, very important, is the resolving power. So it is the ability of the microscope to differentiate very closely situated points as a separate one. So it is the ability of a microscope to differentiate very closely situated or closely placed points as a separate objects. So resolving power of human eye is 0.25 millimeter, and in case of light microscope it is 0.2 micrometer, and it is in electron microscope it is 0.5 nanometer. Electron microscope is having a very high resolution power. As I said, it is the resolving power of electron microscope is 0.5 nanometer. Next important term in microscopy is the numerical aperture. So numerical aperture of a lens is the ratio of the diameter of the lens to its focal length. So it is very much essential in order to understand the magnification, resolving power of a microscope. So everyone should understand what is a numerical aperture. So numerical aperture of a lens, it is dependent on the refractive index, that is the n. It is written or indicated by n, refractive index of the medium. So for example, if a lens is placed in air, so refractive index of air is always 1. Then the theta, it is the angle of the cone of light entering the objective lens. So these two factors, it is the numerical aperture is dependent on these two factors. One is the refractive index, another one is the theta, which is written as theta, or the angle of the cone of the light entering the objective lens. So objective lens, always it works on air. So sin theta, and the maximum angle can be achieved is 90 degree, and sin 90 is always 1. So no lens working in air can have a numerical aperture greater than 1. So that is the general thumb rule. So immersion oil, in case of immersion oil, what happens when we use immersion oil? The numerical aperture is increased. So, and thereby in case of oil immersion objective, when we use oil immersion objective, we get a higher resolution, because the oil is having a higher refractive index, and thereby it increases the numerical aperture. So because of this, so ultimately we get a higher resolution or higher magnification. So this equation, as I said, the resolution, the German physicist, he worked on the, he gave some mathematical equations on the resolution of microscope. So according to this equation, it is the resolution power or the minimal distance between two objects that reveals them as a separate. Means in other words, it is the resolving power of the microscope. So it is basically it depends on the wavelength of the light used to illuminate the object, and the numerical aperture or the n sin theta, which is the numerical aperture of a lens. It is always uh, calculated, or it is written as n sin theta. So which is in otherwise numerical aperture, we can for better understanding, we can say that it is the ability of the lens to gather light. Means numerical aperture, in other words, it indicates the ability of the lens to gather light. So as per Abbe's equation, so the d, which represents the minimal distance, in other words it is the resolution. So it is the formula for calculating the minimal distance is the 0.5 into lambda, means the wavelength of the light, divided by the numerical aperture or n sin theta. So when the d or the minimal distance is smaller, so that indicates a better resolution. When d becomes smaller, when the wavelength of light used is decreased. If we use a light having a wavelength, a shorter wavelength, in that case the numerical aperture increases. So that is why finally the d will become smaller. So the greatest resolution in a light microscope can be obtained by using a lens with the largest possible numerical aperture and light of shortest wavelength. This is the point to be remembered. So in case of light microscope, so greatest resolution we can obtain by using a lens which is having a highest possible or largest possible numerical aperture, and along with a light of the shortest wavelength. If these two points are uh, considered or taken into consideration, so we will be able to get the maximum resolution or greatest resolution when we will be using a light microscope. Now coming to the types of microscopy. So types of microscopy, it is basically of two types. First one is called as light microscopy, where we use visible light as a source. Then second type is the electron microscopy, where instead of light, a beam of electrons are used to illuminate or for getting the image of the object. So under light microscopy, there are different different types of light microscopy. So first is the bright field microscopy, then dark field, phase contrast microscopy, fluorescence microscopy, DIC microscopy, and confocal microscopy. These are different types of light microscopes available as of today. Again, electron microscopy, it is also of two types. One is called as transmission electron microscopy, which is used for studying the internal structures, and scanning electron microscopy. It is for understanding or studying the surface details. Now, what is bright field microscopy? So, whatever ordinary microscope we use, it is a bright field microscope, and it forms a dark image against a brighter background. So, light source is used, and a mirror or an electronic illuminator it is used, and this type of microscope is routinely used to examine both stained and unstained specimens. So in a light microscope, we have different objectives. Four different types of objectives are there: scanning, low power, high power, and oil immersion objectives. So each of the objectives, they have different properties like magnification, numerical aperture, focal length, working distance, resolving power. So each objectives, these properties are different. So it is listed in the table. So total magnification power of a light microscope, as I discussed earlier, it is calculated by the multiplying the magnification of the objective lens and the magnification of the eyepiece. Next type is called as dark field microscopy. So dark field microscopy allows a viewer to observe mostly the living unstained cells. Dark field microscopy is used for viewing the living cells which are unstained. The background, a hollow cone of light is focused on the specimen in such a way that unreflected and the unreflected rays do not enter the objective. So only light that has been reflected or refracted by the specimen forms an image. So field surrounding the specimen appears black. So background of the specimen, it is not illuminated. There will be a dark background against which the object is brightly illuminated. So as the background is it remains uh, as a dark, this type of microscopy is called as dark field microscopy. So this is the path of light in case of bright field and dark field microscopy. Next type is phase contrast microscopy. So here different light passing from one medium to another. So when there is a change in the phase, so this is taken into consideration. So refracted light and the refracted light, these different lights are lights which are said as to be in a different phase. They are finally gathered to form an image, and this image, when the image is formed, so this lights which one type of light is called as in phase or other type is called as out of the phase. See, both these lights are gathered, or uh, a special type of condenser is applied having some annular rings. So both types of lights are gathered through the condenser, and an image is formed where the in phase light, in phase light, it will be uh, and sometimes this phase contrast microscopy is also used for detecting some special structures in bacteria. Then next type of microscopy is the differential interference contrast microscopy. This is again similar to phase contrast microscopy, but here this type of microscopy, it creates the image by detecting the differences in the refractive index. It is not uh, differentiating based on the phases of the light. So it creates the image based on the refractive index of the medium as well as the thickness. So again, another difference with phase contrast is that here two beams of lights are used, two beams of lights are focused, and a prism is placed which splits each light beam, and this with the help of this prism, so contrasting colors of the specimen can be obtained. So the resolution of this microscope is higher than the standard phase contrast microscopy. It is said to be in a uh, more advanced form, and the images, these are brightly colored, and images formed by the differential interference contrast microscopy, it is of three-dimensional in structure. So this type of microscopy is also called as Nomarsky microscopy. Another name of DIC microscopy is Nomarsky microscopy. Then the fluorescent microscopy. Here the object, it is level with some fluorochromes. The fluorescent microscopy, it takes the advantage of the fluorescence, uh, means this is a phenomena which wherein uh, it is the ability of some substances to absorb the wavelength, short wavelength lights, and to release the light of longer wavelength. This is called as fluorescence, and this microscopy utilizes the phenomenon of fluorescence, wherein the objects are level with or stained with some fluorochrome dyes, and it is illuminated with some UV rays. So upon illumination by UV rays, these substances, the fluorochromes, they get excited and they emit lights of longer wavelength. So these uh, lights are captured and they are utilized to form some images. So commonly used fluorochromes include FITC, fluorescein isothiocyanate, and rhodamine. These two are the most commonly used fluorochromes in the fluorescent microscopy. Next is the confocal microscopy. It is said to be the more advanced type of imaging technique. It provides three-dimensional structure, a very high resolution of the specimens. So here a laser beam is used. A laser beam lens focuses a laser beam to illuminate the uh, object in different planes, in a vertical planes, and each of the specimen is illuminated in different planes, and so that a better resolution image can be formed. So this is advanced microscopy, and mostly this type of confocal microscopy is used for uh, obtaining three-dimensional images of the cells and cellular components. Next is the electron microscopy. So it is here instead of light, a beam of electrons are used, and with the help of these electrons, the specimens are illuminated, and it provides a significantly very high resolution and magnification in comparison to light microscopy. So two types of electron microscopy are there. One is transmission electron microscope. It is the images are mostly produced from the radiation that has passed through the specimen. That is the transmission electron microscopy. And the scanning electron microscope, it works in a different manner. It produces the image from electrons released from atoms on the object surface. So the principle of working uh, or principles of operating both transmission electron microscopy and scanning electron microscopy, they are different from each other. So these are some of the photographic plates of different types of microscopy: bright field, dark field, phase contrast, and fluorescent microscopy. So next part of this discussion is the micrometry. So it is the science where we need to where we uh, need to take some measurements or dimension of the microbes. So here the device which is used to get the measurement of the microorganisms, it is called as micrometers. And the entire or the science wherein these micrometers are utilized for getting the measurements, it is called as micrometry. So two types of micrometers are there. One is stage micrometer, another one is ocular micrometer or ocular meter or ocular micrometer. Then stage micrometer, it is fixed on the stage, and it is a slide. It is simply just like a glass slide. So where it is having a scale, and the scale measures 1 millimeter and it has different divisions, and each division it is 0.01 millimeter. Means 1 millimeter is divided into 100 small divisions, and 1 millimeter or one division of stage micrometer, it is equivalent to 10 micron. 10 micrometer, one division of stage micrometer, it is equivalent to the 10 micrometer. Next type of micrometer is the ocular meter or ocular micrometer. It is fixed in the eyepiece. Then it is also having some divisions. So usually 50 to 100 divisions are present in a ocular meter. And the working principle, we need to calibrate both the micrometers. So first we'll have to insert the ocular meter, then we'll have to place the stage micrometer, then we'll have to align by focusing both the scales, and number of ocular division matching with the stage divisions needs to be uh, uh, find out. Then we'll have to find out or calculate value of one ocular division, which is calculated by length on the stage micrometer divided by ocular divisions. This is the calculation which is applied for calculating the size. Now applications for studying the microorganism size, different size calculation, then measurement of cells, pores, and other microscopic structures, and for various research purposes in microbiology, cytology, and material science, this micrometry is very much applicable. So this is all about I wanted to discuss for today. I hope the informations I have included here will be helpful for you. So if you find these informations are helpful, please subscribe to my channel and give your comments so that I can improve further by incorporating more informations on each lecture. So with this, thank you very much. Bye bye.